Hi folks, welcome to Module 4. This week is going to be a great week. We get to talk about two of my all-time favorite topics, which are eclipses and phases of the moon, and then we get into the history of astronomy. So this is going to cover the rest of chapter 4, and then we're going to get into a little bit of the history, which is our next topic. It's a big topic, history, so I want to launch into it a little bit this week, and then we'll finish it up with the next week. So let's take a look at Canvas and get going here. So we're going to start out talking about the phases of the moon, and I want you walking out of here being able to look at the moon and go, ooh, first quarter, third quarter, waxing gibbous. That's always fun stuff. There's a study guide, as always. There's a study guide, and remember, that is your second instructor. And so those are keyed very, very carefully to the textbook. The study guide for this time, because we are going to be working a little bit in chapter 4, remember those section numbers are going to key you directly to the sections in the chapters, and then we're going to launch a little bit into history, so this is definitely going to span a couple chapters. Please pay attention to those chapter and section numbers when you do that. Then we're going to talk about solar and lunar eclipses, always exciting, always fun. Scintillation. Scintillation is basically twinkling. And what's more fun than twinkling stars? Then we begin a discussion of the history of astronomy. Aristotle, Copernicus, the sun-centered and earth-centered model. Why did people think the earth was the center of the universe? And then how did that change? Two of the most interesting characters in the history of astronomy, Tycho Brahe, or Brahe, depending upon how you pronounce it, and Johannes Kepler. The lab this week is a power-packed one, and we're going to talk about a lot about that in a moment, and then our constellations and our quiz. So let's go to that lab right now. When it comes to the lab, you're going to be playing with and trying to hopefully understand the phases of the moon. You're going to need a light source to represent the sun, and then a model Earth and moon. And these can be done with balls, and if you don't have sports balls floating around like tennis balls and baseballs and things like that, heck, you can use rolled up balls of socks and pieces of fruit, whatever you've got floating around the house. Now, the first one is, I want you to start understanding how night and day occurs. And you might go, Mary, I get this. I totally get this. But pick a window or a light with a lampshade on it so it doesn't hurt your eyes. And then I want you to rotate slowly around and pay attention to where the sun is compared to your nose. So if you're looking straight ahead, the sun is directly in front of your nose at A, and then as you move to B, where's the sun? And if you're facing direction C, where is the sun? Well, I'll give you a hint. When you're facing direction C, the sun's going down. And when you're facing E, you can't see the sun anymore. So I want you to understand the mechanics of what's going on here. The sun is not the thing that's moving. All of this change in night and day is occurring due to the rotation of the Earth, and I want you to rotate your little head around and see if you can make sense of this and put these positions in relative to that. We're going to use a couple different simulations from the University of Nebraska. Again, remember, you have to change browsers or definitely use that Flash player to do them. So let me explain this first one a little bit. We're going to start out not moving the little fellow, but I want you to understand by coloring in the circles exactly how the phases of the moon occur. Now, remember back up here that when your nose was facing the sun, you could see the sun. When your nose was facing this direction, you could not see the sun. It basically means that the moon does not get lit up by the sun all the time. So if we take our little pretend guy, you can grab him and put him over there. It doesn't matter where he is to start with. This is the moon, and you can pick up your little moon in this simulation and move him anywhere you want. But if you look at just the moon, notice the dark half, the black half of the moon is always dark. Well, as you draw your pictures on the lab, notice no matter where I move the moon the back half of the moon is always dark. That is a big deal, folks. Big, big, big honking deal. Now, notice in this picture up here, the phases change because that's what we see from the Earth. We see all these different phases. But when you go back to here in the lab, please notice that the dark half, every one of these back halves of the moon is dark. Why? Because the sunlight's over here. And so please color in the back half of every one of these circles dark. Because if it's the sunlight's not hitting it, honey, it's dark. Okay, then as the moon moves around, here's the cool thing. From the perspective on the Earth, and perspective is going to change depending upon where you are on planet Earth, so it doesn't matter the humans. We see the same phases of the moon if you happen to be in North America or Asia or Outer Mongolia. I guess that is Asia. So we don't care where this guy is right now. We care about the moon and its relationship here. But if you start out here, we have a new moon. And as the moon goes through its rotation around the Earth, watch what happens. What we see from the planet is only the bit inside of the big round circle. So from the Earth, we see just the bit that's this little slice. See that little tiny slice? It's like a little slice of pie that's inside that round circle. And that little slice of pie is this little slice of light. And you go over here, what do you see? Well, you see just a quarter of the pie. We see a quarter moon. You go over here, we see from the Earth, we see half of the moon, and this is what we call the full moon. We see the bit of the moon that is lit up by the sun. As the moon rotates, the moon hasn't done anything different. It's just rotating around the Earth. We see the third quarter moon. So what I want you to do in the lab is I want you to rotate the moon around, and I want you to color in the little light slices of pie and the dark half of the moon. And then there's the bit that we just plain don't see from our perspective on Earth, and it doesn't matter where we are on the planet because everybody on the planet sees the same phase at the same time. Okay, then what I want you to do is spend a little time. Can you identify? Remember that stuff from notes about can you identify the phases of the moon? And remember, wax on, wax off. Remember all that stuff. Moonrise and moonset. Go back to your simulation. And when you go back to your simulation, set the person in a situation where he sees a new moon, start the animation, and you can run this kind of slow. If you run it crazy fast, you're not going to see diddly. Run it kind of slow and pay attention to what time does moon rise, what time does moon set. And hopefully you're going to see a lovely pattern. Then move the little person so he or she sees first quarter, sees full moon, sees third quarter, and sees time of moonrise and moonset. And these are your choices. It's multiple choice. Use those to fill that in. And you're going to see a pattern. The seasons. The seasons are fabulous. I want you to build a model Earth. Now, if you have a globe, an old-fashioned junior high, elementary school globe around your house, yahoo, you do not need to build a crazy little pretend globe. I built one out of a tennis ball, 2 rubber bands, and I think that's a bit of tape. And then you're going to label North Hemisphere and Southern Hemisphere. This is an old rotty tennis ball I had around the house. And then that was the top of a little jewelry box that I used to kind of hold it in place. You're going to need a lamp to represent the sun. But one of the things as you do this, you need to keep the Earth tilted. The Earth, as you know, is tilted 23.5 degrees from the plane of the ecliptic. So pick a spot in your room that's going to represent where you keep it tilted. I picked a corner of my office, and I kept this tilted into a corner of my office. You notice this is pointed that direction. This is pointed that direction. And you'll notice my little N for North America in this situation, see how bright it is? And when I moved it to the other side, look at the back side. All of a sudden, with the same tilt, not as much light. We'll take a wild guess which of these pictures represents summer and which of these pictures represents winter. I want you to really feel this and get this into your gut. Therefore, I want you to construct this, do this, and take a selfie and include it. Fill this out and follow the little yellow brick road as far as questions go. And then we're going to talk about eclipses. You have your pretend Earth, and that was what you built up here. Use another little ball or whatever you've got floating around. It could be a pencil if you want. But I want you to use your lamp as the sun, your ball as the Earth, and then something else as the moon. And play with the lamp. Can you create eclipses? I know you can find pictures, but can you actually create them and make the shadows go where they go? Sketch the setup of what these eclipses are going to look like here and here. And then be sure to label each celestial body. Go to the Union Seasons Demonstrator. This is a really, really quick and cool demonstration from the University of Nebraska. I really like this one. What they've done is they have taken a series of images once per day out of the same window, aiming in the same direction throughout an entire year. You can watch the snow fall, the snow melt, and the trees get greener and lose their leaves and go away. But what's cool is you can see because of the Earth's tilt, as the location of the sun in the sky changes because of that Earth's tilt, you can see the length of shadows changing. And I want you to watch that and answer some questions about that very cool thing. Seasons and the Ecliptic Simulation. Okay, go back to this simulation. And what I would like to have you do is take this little fella, put him up where we are. Most of us are about 45 degrees latitude here in the Eau Claire area. If you're in a different part of the world taking this class and you want to set him at your latitude, cool, you're welcome to do that. And then I want you to move the Earth around. And as you move the Earth around, notice the change in tilt. Notice the change in tilt here, and notice the angle at which the light hits the ground, and answer the questions accordingly. Last but not least, an eclipse simulator. The eclipse simulator is from another source, not from University of Nebraska. And what I'd like to have you do here is you can go from solar eclipse to lunar eclipse, and it's all celestial mechanics. Where is the Earth and the moon and the sun? And it all has to do with one orbiting the other and how we view things. So follow the little yellow brick road, fill in the blanks, and I want you to have experience with this. The simulations are really a great way for you to get some hands-on experience and manipulate things and hopefully get some of this stuff into your soul so you really understand what's going on. If at any point in time you have any questions, please be sure you holler. This is a great week because I love the moon and eclipses, and who doesn't love a good eclipse? Have a grand week. We'll talk to you soon. Bye-bye.